Hello mathematicians, we're now going to have a look at primitive functions, which is our introduction to the process ultimately of integration. So with primitive functions, if we know the differential of a function, we might be able to find something about the original function, basically by undoing the differentiation, or called, as it's called, the process of anti-differentiation. So this is the process of finding the primitive function. So the primitive function of little f of x is sometimes written like this, but as we'll see later on, this is a fairly specialised case. What that represents is the family of curves which only differ by a constant and which would all differentiate down to this particular function. So if you look on the right here, you can see that all of these curves, all of this family of parabolas, would end up differentiating to give us y dashed equals 2x. So if we are going to find the primitive function of y equals 2x, it could be any of those curves there. So what we have to do is to recognise that we are talking about a family of curves. So the primitive function of f of x equals 2x is written as f of x equals x squared plus a constant. And depending on the application, we may or may not be able to find that constant. So let's have a look at this in practice. So in general, the rule for finding the primitive is that if dy dx equals x to the n, where n is not equal to minus 1 for reasons which we'll come to later on, then y equals x to the n plus 1 divided by n plus 1, plus the constant, where y is the primitive function and c is the constant of integration. So you will recognise that despite them trying to disguise it, this just means undifferentiate. So whatever we differentiated to give us x to the n must have been one power higher, and we must have ended up multiplying by that n plus 1. So now we have to divide by it so that we're back where we started. So if we get some extra information, such as a particular value that the function must pass through, so that is the coordinates of a point on a curve, we can find the particular primitive out of the family of all possible primitives. So for example, if y equals x squared minus 1 was the curve which was differentiated, then the differential, the derivative, is dy dx equals 2x. And if somebody says, well, now integrate or find the primitive of 2x, then the best we can do is say that the primitive of 2x is x squared plus c. But if we know that the original curve had to pass through a particular point, then we can substitute that point in and find what the value of c actually is. So we know that x squared minus 1, for example, has its vertex at 0, minus 1. So if we plug that pair of values into y equals x squared plus c, we'll get that minus 1 equals 0 plus c, so c equals minus 1. So the actual curve, which is the one out of the family of primitives, is y equals x squared minus 1. It actually sounds a lot more complicated than it is. So all that we really have to do is think that we're doing the reverse of differentiation and realise that that can't pin us down to one particular answer unless we're given more information. So let's have a look at this in action. So for each of these we're going to find the primitive, so the family which could have differentiated to give us this result. So using our rule, x squared becomes x to the n plus 1, so x cubed, and we divide by n plus 1. So we do that for each term, and we have to add our constant of integration. If we don't do that, we're giving an incorrect answer, because the best we can do at the moment is get the family. So I'll just quickly run through these. So always following that same rule, up the power by 1 and divide by that. So that gives us our next one here. On this one here, when there's no power of x here, we know that that really means x to the 0. So when we raise that by 1, that will become x to the 1. But we also know that we came across that when we differentiated. If we differentiate 3x, we'll get 3. So minus 4x becomes minus 4x squared, and on 2, 16x to the 7 goes up to 8, and we divide by the 8, plus our constant of integration. And then we just simplify that, of course. So we get our final expression down here. Now, for the next example, we're given the differential and we're asked to find y as a function of x. So it's just another way of them asking for us to find the primitive. So the primitive is, applying our rule, x squared plus 3x plus c, and if they give us some information, we can find c. So if y equals 3 when x equals 0, y is 3, put in our values of x as 0, and we can see that c must equal 3. So y equals x squared plus 3x plus 3. And if it was on a different curve, so y equaled 8 when x equaled 1, we do the same process, we discover that c is 4, and our curve then is y equals x squared plus 3x plus 4. Now, moving on, what we can do is that we can cope with linear functions which look a little bit more complex. So if we have dy dx equals ax plus b to the n, and again, where n is not equal to minus 1, then we can undifferentiate that by saying if we raise the power to n plus 1, we'll divide by that n plus 1, but we'll also divide by the differential of the brackets, and we'll add our constant of integration. So if we look at these examples here, to find the primitives of these, then if we have, for example, 3x plus 1 to the 4th, we'll raise the power to the 5th, we'll divide by 5, and we'll be dividing by the differential of the brackets as well. And we'll be adding our constant of integration. So likewise, our next one, add 1 to the power, divide by that, divide by the differential of the brackets, add our constant. When we have our next one here, we've got a negative index, the rule works just the same. So we add 1, which takes us to minus 1, and we divide by minus 1. And if I then rewrite it back without the negative index, I'll just have minus 1 over x plus 1 plus c. And for our last example here, where we'll have a fractional index, again, the rule works exactly the same. So I'll add 1, I'll divide by that. I would divide by the differential here, as up here, but it's only a 1. So then when I write it back in the original form, I've got 2/3 times the square root of x plus 1 cubed. So let's have a look at this example here. So we're given the second differential, and we're told conditions about the first differential and the original function. So if we find the primitive to begin with, so raising the power by 1, dividing by that power, dividing by the differential of the brackets, add our constant, then we have that f dashed of 0 equals 0, which means that when x equals 0 in this expression, 0 is the resultant. So we plug those numbers in there, and we've got minus 1 cubed on 6 plus c, so c is a 6th. Now we start from this, and we integrate again, or find the primitive again, just using our same formula. The 6th becomes x on 6 plus our constant of integration. We know that when x equals 1, f of 1 is 0. So we do our substitution into here and find our new value for c, so that we then have the overall original function.